right, welcome everyone. So today I'm happy to welcome Dr. Colin Forsyth from UCL's Mullet Space Science Laboratory to present for us today. Colin's research interests are in substorms, radiation belts, and space weather. He did his PhD at the University of Leicester and moved to MSSL in 2008, where he's been since. As part of an ISI team led by Dave Knutson, Joe Borowski, Toma Carlson, Ryu Kotoka, and Nura Partimis in 2008. I hope I got all those names right. Colin led the group in reviewing the physical processes of mesoscale aurora. And it is this work and this research overview which he will be talking about today. So with that, Colin, if you would like to start.
Thanks, Kyle. Hopefully you can all see that now.
Yep.
Great. So thank you for inviting me to come and talk today, and thank you for all being here. As Kyle mentioned, this talk is on it's a review or an overview or a review that we did a couple of years ago, coming out of an ISI workshop, and Kyle ran through the organizers. So a big thanks to them for organizing that and for all the participants in that workshop. It was a really fascinating week where we went back through and we didn't try to update the ISI book from 2003, but rather advance on that. Instead of looking at the physics of the aurora per se, actually looking at the physical processes, out in the magnetosphere that might drive the aurora and the different auroral forms. The review is listed down here, so you can find all the details there. If you follow this QR code, which I'll leave on the screen for a few more seconds, that will take you to the review. This talk is going to be an overview of that review, so there's far more information in that paper, and that will also link you into the other papers that came out of that workshop on the different areas of the aurora that we concerned ourselves with. So as well as the organizer of that workshop, I'm going to thank the co-authors who worked with me on this review paper. I have put this review or this overview together since we did that work, and so I absolve them of any responsibility of anything that I might say in this. If they agree with me, great. If they don't, then it's all on me. But yeah, do go and have a look at that review paper, and that will give you far more details than I can go through in the next 45 minutes or so. So, as I say, this workshop that we went to concentrated on these various different aspects of the aurora, and these have been captured in this image, this overview image by Megan Gillies. And so we looked at all these different areas, such as the quiet, discrete auroral arc, which I was surprised to find we still have a number of questions on, despite that being the sort of the fundamental auroral process that we consider. Then we consider things like the small scale dynamic aurora, the diffuse and pulsating aurora, such as you see from precipitation of the high energy particles, the area that my team looked at, which was the mesoscale dynamic auroral forms, and then there was things like the proton aurora and subauroral forms, the dayside aurora, so things like photoaurora, field line resonance arcs, polar cap aurora, and polar cap features. And so largely we've tried to separate these different areas based on the phenomenology and try and keep them separate, even though there is some overlap between them. And we'll see particular things like the diffuse and pulsating aurora features in some of these dynamic auroral forms that we're looking at. But largely, this is what I'm going to be focusing on in this talk today. So these forms, largely night side forms and associated with various different activity in the magnetosphere. Now, one of the hardest things in doing this is actually defining what we think of as a mesoscale aurora. And so we came up with this rather generic definition of dynamic auroral forms with scale sizes in the range of tens to hundreds of kilometers. But really, that's not always particularly helpful, because that could encompass quite a lot. So we are looking at the phenomenology of this. And so the features that we considered to be the mesoscale aurora that we were going to look at, things like auroral streamers, polar boundary intensifications, auroral beads, omega bands and the torches, and then giant undulations. And the things that it wasn't, which is also a useful thing to consider, are all these features on the other side. So the quiet arc, the polar cap features, pulsating aurora, dayside phenomenon, and the proton and subauroral features. As I mentioned, those are all covered by different reviews in an overall volume, but it's these ones in black that we're considering as the mesoscale aurora that we were interested in. So let's start from the top and work our way through. And we're going to start with these auroral streamers. So a lot of these definitions go back quite some time into the early observations of the aurora. And auroral streamers were originally defined as having a north-south orientation. And so if you see this image from the Henderson et al. Paper in 1998, I'm just going to see if I can get up my little... So you can see here we have this feature. It stretches across the auroral oval from one side to the other and is roughly north-south aligned. But we can also see that these features that stretch across the auroral oval can end up being more east-west aligned, particularly in different parts of the auroral oval, as seen in this data from the Sergeyev et al. Paper in 2005. And so we now generally consider that an auroral streamer is this narrow auroral form which stretches across the auroral oval from the poleward edge towards the equatorward edge. They're very narrow features, typically less than 100 kilometers wide, and we do see them following the convection flow lines. They're also typically associated with fast plasma flows, flows exceeding 1 kilometer per second in the ionosphere, and a distinct region 1 type field line current system. And so we can see some of these, we can look into these in more detail. So this is a paper from Am et al. In 1999, where they used the SECS method to look at this auroral streamer as it passed over the Miracle network. And here you can see the brightness of the auroral streamer, and then these crosses and squares give you an indication of the current system. So we have this upward current system within the aurora itself, and then this downward current system to the dawnward side, giving us that region 1 sense. And one of the interesting things that came out of this study is that the currents associated with the streamer itself are generally more intense than the downward field line currents that come in the region off to the dawnward side of that. We also see these equatorward plasma flows are associated with the auroral streamer, and this is results from Gallardo-Lacour et al. In 2014. We can see these red flows from the Superdan radars indicating the flow equatorward associated with the auroral streamer itself. But there's also, to either side of the auroral streamer, this region of blue flow, which is actually poleward or return flow in the ionosphere being set up as well. So it's not simply just this equatorward convection stream. There's a poleward convection stream here as well, as you would expect if you looked at the convection around these field line current systems. So we expect to see the flow coming through the streamer and then being diverted around the sides and returning to fit this current system. And not only do we see this in the ionospheric data, we see this in overpasses. So we have here data from a Sergeyev et al. Paper looking at the DMSP spacecraft as it passed over, actually conjugate to an auroral streamer. The auroral streamer was observed in the other hemisphere. And looking at the magnetic field perturbations, there was an upward and a downward current system. These are flipped the wrong way around compared to this because the spacecraft crossing was through this downward current region first. And then in between, if we look at the E cross B drift velocity, we can see this convection stream, and we can see part of that return stream as well. And so if we take all of these features and we think what they might look like if they were mapped out into the magnetosphere, then we have this region 1 type current system and associated with this long stretched out region in the magnetosphere. And so typically we think these auroral streamers are associated with something long and thin that's moving through the magnetosphere, and it's generally accepted that it's burst-deep bulk flows that are the driver of these streamers. And so we have this accepted manifestation, or acceptance that the streamers are a manifestation of these fast and localized flow in the plasma sheet. And this just shows a couple of examples of papers out there. So Nakamura et al., where they had observations from geotail. You can see the mapped location of geotail is close to this auroral streamer, and at around about the same time as that, it sees this enhancement in the flow, and that's an enhancement in the convection as well, that can be seen in the electric field, also associated with a dipolarization of the magnetic field within that flow region. A similar result from myself and co-authors, where we used the cluster spacecraft, cluster again mapping very close to this auroral streamer. We see the fast flows, and we even managed to use the kilometer technique, the force spacecraft, to get an idea of what the field line currents were. This flow is actually made up of two flow bursts, each associated with one of these upward and downward current systems. And that gave us that region 1 type current system that we expected to see associated with the streamer. Then finally, results from Pitkin et al. In 2011, again using data from cluster, we see this correlation, or this coincidence of these fast flows at the time the spacecraft was conjugate with an auroral streamer. And in this case, they also had data from the IceGap radar, so they could see some of the flows and also see some of the hot plasma coming in associated with that. And so we really do think that these streamers are associated with these flows as they pass through the magnetosphere. Now, this has implications for later on, and so I wanted to take you through this case study published by Sergeyev et al. In 2000. Here we see the streamers in the data from the polar spacecraft, so we can see these north-south or more or less north-south aligned auroral features. And these auroral features actually ended up being approximately conjugate to observations from geotail. So geotail out in the magnetosphere observed what we've seen in the other spacecraft data. So we've got this enhancement in the velocity of the plasma associated with dipolarization of the magnetic field. So we've got this bursty bulk flow type feature associated with the streamer. At lower altitudes, we have an energy dispersed proton injection seen by interball aurora, and that was up here. And actually, if you trace these injections back to work out where they were coming from, then the time at which those injections should have started is approximately in agreement with the times where we see these dipolarizations at geotail. And then interestingly, we have data from LANL spacecraft at GEO. So LANL is right down here. And again, associated with these flows, we see an injection of hot plasma, energetic plasma into the geosynchronous region. Now, these are, as we've sort of gone through our development of the ideas of fast flows in the magnetosphere, these are not really a surprise to anyone now, but actually being able to link the streamer with activity both in the magnetosphere and potentially getting into the geosynchronous region and beyond is going to be useful later, as we think some of the flows, some of the processes associated with the streamer might also be associated with other types of dynamic aurora. I will just say something here that this reminds me of a comment that Eric Donovan made when I gave a shorter version of this talk at AGU. If I trip up and say that one type of aurora causes another, then that's not in fact the case. It's the processes behind the aurora that lead from one into the other. It's not that, for example, a streamer then goes on to cause something else. It's that the processes behind the streamer cause that. So we have some open questions with regards to auroral streamers. As we've learned more about them, we've looked in more detail at things like the individual flow bursts. You'll also see descriptions of dipolarizing flux bundles and kinetic scale or ion scale current systems associated with that. And so we have this question that if we have these very small scale features associated with the flow bursts, should we also see this appearing as some kind of localized brightening within the streamer? And can we get a handle on that? We see these streamers persisting for a particularly long period of time, tens of minutes, but we're seeing that these flow bursts generally or these bursty bulk flows as they pass the spacecraft are lasting for around about 10 minutes or so. So how do we get these streamers persisting for long periods of time? Can we have these long flow channels that just keep passing more and more plasma into the inner magnetosphere? There's another question. If we look at things like the simulations, for example, this paper by Wiltberger et al. In 2015, that suggests that we might see lots and lots of these bursts of high velocity plasma coming in. And so how many streamers should we expect the magnetosphere to produce at a given time, and how many do we actually see? I don't think we really have a handle on that yet. And then finally, and I'll touch on this as we go forward, what is the quantitative link between the processes that drive the streamers and other magnetospheric phenomena? Okay, so that's streamers. Now going to move on to something that's sort of related to the streamers, and that's these poleward boundary intensifications. So again, like so many of these, we've seen reports of activity at the poleward edge of the auroral oval throughout the literature. But really, in terms of the definition of poleward boundary intensifications, we go to this paper by Zester et al. In 2002, and they defined these PBIs into two different classes. Well, actually, they called them three. I'm compressing two of those classes into the same one, and that's a class where we have something which starts at the poleward boundary and then propagates across the auroral oval, either in a north-south or east-west direction, essentially becoming an auroral streamer. And there's another form of PBI, and this is sort of seen in this image here, where we get these spatially periodic brightenings along the edge of the auroral oval, and they really just stay there. You sometimes get these forming into auroral swirls, but they don't evolve into something that propagates across the auroral oval. Now, one of the interesting things is that this distinction between class A here, the polar boundary that then propagates across the auroral oval, and an auroral streamer is unclear. So when can we call one a PBI and when does it become a streamer? And that's problematic for some of the observations that we have. And just in terms of when and where do we see these things, then we do get reports of PBI activity at all levels of geomagnetic activity. So if you want to understand what the physics of the processes behind the PBI are, then what you might want to do is take observations of the precipitating particles. And that's one of the few ways where we can be sure that we are actually seeing something associated with the PBI. If you fly through it at low altitude, then you're fairly certain that whatever plasma you're seeing can be linked to whatever auroral forms you are seeing. And so this is a set of observations from the Cascades 2 sounding rocket, and these were published by Mella et al. In 2011. Here we see the path of the rocket passing through this poleward boundary form, this sort of broken up poleward boundary form, and looking at the electron spectrogram in this region taken from the rocket, then we see that we've got fluxes at all energies of electrons up to around about a keV, suggesting that we've got some kind of alphanic, this is a broadband electron process or signature, and so we've got some kind of alphanic process bringing those electrons down. Now, this is not necessarily a unique feature. It does tell us something about it, but again, one of the problems with doing these observations using just the rocket is that we get one pass through it. And that doesn't really tell us about the time evolution of what's going on here, not over large timescales anyway. So for that, we'll look at data from a paper by Hull et al. In 2010 using the cluster spacecraft, when the cluster spacecraft were close to perigee, so passing very rapidly through the inner magnetosphere. And at this time, they actually passed over this region where we saw a PBI in the image spacecraft. And they were aligned roughly in a string of pearls, so passing through this region one after the other. And looking at the data from the electron spectrometer, the PEACE instrument on cluster, we see the plasma sheet electrons to start with, and then we see this region of more broadband electrons thought to be associated with alphanic wave activity. So this is a sort of two distinct regions seen by the spacecraft on its first pass. The next spacecraft through sees an extension of this hot plasma out towards where the Alphanic activity was. And by the time the third and the fourth spacecraft have passed through, we're seeing this hot plasma everywhere, and we're seeing very little of this Alphanic activity left. And so what we're seeing here seems to be the evolution of this auroral form being associated with Alphanic activity, and then later into a more quasi-static or typically hot electron population from the plasma sheet. So if you want to think about what the magnetospheric driver might be, as mentioned earlier, we've largely focused on north-south or east-west types of PBIs, i.e. these are PBIs that evolve into auroral streamers. And when we look at the measurements from these conjunctions where we have PBI activity going on, we do indeed see, again, these fast streams that we would have associated or would associate with bursty bulk flows. The difficulty is, if we're making these measurements well within the plasma sheet, then can we really say that this is related to what's going on at the boundary? This is not a measurement from the boundary of the plasma sheet. So if we're treating the edge of the aurora as the open-closed field line boundary, then seeing something that's well within the plasma sheet, we're not seeing stuff at this boundary. And so at what point do we have to just say that this is streamer activity? This is the PBI evolving into a streamer. And if we take, say, this cartoon image from Sergeyev et al., we can start to see the problem here, that if your BBF is disconnected from whatever is going on further out in the magnetosphere, then you're not seeing something that's really this PBI activity anymore. You're seeing something within the plasma sheet. Now, we can attempt to try and see where this activity might be coming from. So this is a study by Zester et al., where they took data from, I believe this was the image spacecraft, and mapped it out into the magnetosphere to see what that would look like. And indeed, you do see these long forms that look somewhat similar to the cartoon that Sergeyev et al. Put forward. But this does bring us on to a problem that we have, and that's with mapping anything, particularly towards this poleward edge of the aurora. So just as an example, what I've shown here is the crossing distance of a field line, if you map it out using the Cyganenko model at different latitudes. I've just done this in GSM rather than in magnetic coordinates, but this essentially tells you the latitude above the magnetic equator. And you can see that as we go through up to about 40 degrees or so, we're covering the inner magnetosphere. We then, at around 46 degrees, get a jump where there's a very small range of latitudes correspond to about 20 RE of field lines crossing the tail. And then we get this exponential increase as you go up of the tail crossing distance as you go up with latitude. And so mapping anything out from this region is very difficult. And then if you throw in another current system, such as we see here from Nikolaev et al., if you throw in something like the substorm current wedge, which distorts that average picture of the magnetosphere, then that mapping gets even worse. And you can see here these sort of red field lines or red contours show you where a set of field lines would have mapped to start with, and then these green ones show you this new mapping, and you can see that field lines that were much closer in are now, the poleward much higher latitudes are mapping to a very different distance. So if we can't necessarily do this using observations from the plasma sheet, can we maybe get some more information from the ionosphere? And we've got this study by Zhu et al., where we actually see, in advance of the PBI being ignited, we actually have this enhancement in the polar cap flow. So we're seeing flows coming across the polar cap, and maybe that's some kind of cohesive structure coming across the polar cap, which is then interacting at the edge of the polar cap to create some kind of boundary intensification. And in fact, this study by Atani et al. Suggested that one of the ways that this might happen is simply because you've got this fast flow, or this polar cap flow coming in and hitting a region where you've got a change in conductivity, because as you move from the polar cap into the auroral region, you have this enhancement in conductivity, and that might allow you to get some kind of features happening here. The issue that I have with this is that at some point, in order to get across that boundary, if we treat that boundary as the open-closed field line boundary, we do have to invoke reconnection in order to get these field lines coming across that boundary to get other things happening. So there's probably some coupling going on here between the ionosphere and the magnetosphere, but it's not as simple as looking at one or the other. The other issue that I have with this is that we might have some flow passing over, and we can see this in the ionosphere data. We've got something which happens in the magnetosphere and gives us some coupling back, and we see particles coming down to cause the aurora. But what's going on the other side? Is it necessary that if we've got a fast flow in one hemisphere, that we also have a fast flow coming to the same place on the other side? And if not, should we be able to see some of these PBIs that occur without this fast flow being seen in one hemisphere, because it's actually a fast flow from the other side? So again, we have some open questions here, and we're looking at things like how the intrusion of plasma, reconnection, and feedback are all related, what the links between the flows, different instabilities, and different forms of precipitation are. Do we have to have a PBI preceded by an ionospheric flow signature, or can we have it from one side, see it in one polar cap and not the other? One of the big things that doesn't seem to have been addressed is these spatially periodic features, the ones that do not propagate equatorwards. And how can we get these? If they're not associated with these streamers, then what's the thing that causes those? And then finally, if we want to make headway on this, how do we make observations at the boundary of the open-closed region at the right time in the magnetosphere? And that's a very difficult thing to get done right. Okay, moving further inwards now, we're going to look at auroral beads. Now, these were originally described as azimuthally spaced auroral forms, more typically described as auroral beads, I think following the launch of the Themis array of all-sky images. And so these spatially periodic forms, and you can see examples of them here, taken either from the image spacecraft, from the ground in the all-sky images, or taken here from the International Space Station. These are typically seen around about the time of substorm onset. They form on an equatorward arc and have scales of around about 1 to 100 kilometers or so. Now, in terms of their scale, this is something that we have to be a little bit careful of, because if you look at this, it looks like there is a given scale to these things, and that might be of the order of hundreds of kilometers. But actually, if you take this and take a brightness cut along the arc and do a Fourier analysis of this, we can actually see wave power at a range of spatial scales. So we do see it at the small wave numbers, so the large wavelengths, but we also see down to the larger wave numbers, the smaller wavelengths, we still do have some power here. So it's not just that there's a single wavelength to these things, there is power at smaller wavelengths as well. What we see in terms of how these evolve is that we see a brightening of these over a very short period of time. And if you take the data from, say, the all-sky imager, take the brightness and plot that brightness on a logarithmic scale, you see this nice linear pattern. So we're seeing an exponential increase in the brightness of the aurora. And actually, if you look at this on the individual scale sizes, we see that brightening, that exponential brightening in just about every one of these scale sizes over a similar period of time. And so this is really a hint that this auroral bead feature is being driven by some instability in the magnetosphere. Another hint at that is that if you look at observations from both the northern and southern hemisphere together, then you see very similar features at the same time. And this is a fantastic movie from the Matoba et al. Paper that shows this evolution of the auroral beads seen in both these cameras, one at Showa and one in Iceland, at roughly the same time and in the same way. So we're seeing the same thing. We're seeing something coming from the middle of the magnetosphere and going towards both hemispheres. In terms of what the plasma looks like, if you fly through one of these things, and this is a paper by Matoba and Hirihara, what we see is actually we get this horseshoe-like distribution. It's most clear here that if you look at these pitch angle distributions, we go from 0 to 180 degrees, and then this is electron energy. We have this horseshoe-like distribution. We have energy at these high electrons at these high energies, and then this bite out in the 180 or close to the 180 degree direction. And so this is suggestive of this quasi-static acceleration process, bringing these particles down to generate the aurora. So if we think it's a plasma instability, the question is, which one? We see this exponential growth of waves, and we don't just see that in the aurora, but we also see that in ULF waves on the ground in the magnetic field. So there's a question, which instability have we got going? And this seems to be where we have a little bit of a problem as well, because we can take all of these different instabilities, such as the cross-field current, shear flow, kinetic ballooning instability, and we can find that if we plot out some feature of these beads, we can get some agreement. So we can get an agreement between their speed and their wavelength. If we're looking at the kinetic ballooning instability, we can see an agreement in the growth rate if we look at the shear flow ballooning instability. And even actually taking different parameters for the same instability, we can see sometimes we get an agreement and sometimes we don't. I think what this is telling us is that the parameter space for the in situ conditions is far too wide to either confirm or eliminate a particular instability. And so we need to get a better handle on what the properties are of the plasma at the point at which this instability is going off in order to pin down which instability we should be seeing. Now, I just wanted to highlight this paper because it's, and not just because I'm a co-author on this, but actually because I think this is a really interesting way of taking the data that we have and pushing it even further. One of the things that we can't do in space is deconvolve the temporal and the spatial information. But you can do that when you have an auroral imager because you have a 2D view of what's going on. And so you can transform that data and you can get both spatial and temporal information out of that. And if you do that, and you can do this using FFTs to filter the data in both space and time, you can actually pull out the dispersion relation of whatever you're seeing. So the dispersion relation of the wave that is causing these auroral beads. And this was work by Kelvin et al. In 2018, where they managed to do this. And what we see here is this occurrence of different frequencies against the different wave number. And we get an agreement here with this dispersion relation, which is actually a warm plasma dispersion relation of a kinetic alphane wave. So one of the things that has to be considered is, do our plasma treatments, do our theories actually extend to the correct regime that we're looking at? Because it was necessary to go to this warm plasma extension of the theory in order to get this agreement. So what Nadine and her co-authors were able to show in this paper was actually that it looks like whatever instability is driving some kinetic alphane wave, and that we actually pulled the properties from that of around about a parallel wavelength of 1.8 RE, but a perpendicular wavelength of only around about 500 kilometers. And that's what that would look like if you map that out into space. So we do still, again, have these open questions. And the big one is about the plasma conditions in and around the source region. And what we need is can we use that to rule in or out any instabilities, or can we do that based on the auroral observations alone? I don't think we can. I think we need all of those to be fit together. We also need to make sure that whatever theories we're using of the instabilities are fit to the warm plasma regime that we're likely to see, because these processes are going off right in the middle of the plasma sheet, right in a warm plasma. It is the very definition of a warm plasma in that region. And something which I haven't touched on here, but is still a question, is this a driven phenomenon, or can it occur through something where just the general changes in the magnetosphere, as it interacts with the solar wind, these large-scale variations, can these lead to the setting off of these auroral beads? That's still very much an open question. Sticking with the equatorial aurora now, I'm going to look at these things called omega bands and torches. And this was something where I really had to get my head around the terminology, because I think the terminology has changed over the years. Where we would now refer to an auroral arc, we might have previously referred to an auroral band. So the omega band itself is what we would otherwise call an auroral arc, but this arc with some undulations on it. And the omega features are not, as you might think, these brightenings of the auroral oval are extending poleward, but rather the fact that we see these dark regions that are roughly the shape of an inverted capital omega in the aurora between these features. So these bright features we call torches, and it's the gaps in between that have this auroral shape, this omega shape that allow us to define this as an omega band. And so this is just an example. This was an event originally published by Liu et al. In 2018, but I just wanted to show you this. I've mapped this out in space, but also shown you the original ASI data, and you can see these features. They have this dark region in between and these torches. It's a very dynamic. It's not that they stay the same shape and move through. We've got constantly changing aurora here and all sorts of things going on. And you can even see that within each of these patches, we've got striations, we've got things that seem to be moving and going on within that. Now, if you look through the literature, it's typically reported that an omega band is a feature of the recovery phase of substorms. But there's a rather nice statistical study, and it's one of the few statistical studies actually of the aurora that I've seen that are able to capture some of these dynamic features like this by Partames et al. In 2017. And so they were able to look at the occurrence of these features by looking at how broken up or how wavy the auroral arc was. And by then looking at the occurrence of them, this is the relative to the start of the expansion phase and relative to the start of the recovery phase. Then what they seem to see was actually you do see quite a lot of these during the expansion phase, but the peak in activity is somewhere between the end of the expansion phase and the start of the recovery phase. Taking the data from these and doing a superposed epoch analysis of the various features. So this is of the IL index. It's a localized L index from the image array. We start to see that it's generally happening during active times. So IL getting down to around about -300 nanotesla. But also we're seeing it's a fairly active time in terms of storm-like activity. We're not seeing many that get down and trigger what we would call a geomagnetic storm getting to -50 DST, but our average is getting very close to that. We're well into the -40s here. So this is a storm-like event, even if it's not a storm itself. So, these are going to complicate, if we're trying to map these features out, if we've got this activity going on, we've got the formation of the substorm current wedge and so on, it's going to complicate how we map these back to their source region. And some of the studies of these have been rather wild in where they have suggested that the source regions might be. We do see auroral features within the omega band. I touched on this briefly in the introduction. Within the band itself, we see pulsating and streaming striations of the aurora within the torch itself. And this has been seen in sort of high time resolution TV camera images of the aurora. And you started to see some of that in the ASI data as well. If we look as these things pass over various ground instruments like the ISCAT radars, what we have here is sort of the background, what we expect the energy profile of the electrons to be just in general. This is the profile for the westward traveling surge. And then for these auroral band features, we have this feature here. So we're really seeing this enhancement in high energy electrons coming down. And this again fits with the pulsating aurora, and the pulsating aurora may be having a source region in the ring current. And we can get a similar sort of picture from observations from the cluster spacecraft. This is a study by Wild et al. Here again, we have data from, so this is electron data from cluster 4, which was very close to the inner magnetosphere here. We have the footprint of this as it passes over the superdarn radars. We can see enhanced plasma flows associated with the superdarn radars, and then all sky camera data where we can see this is associated with an omega band. And we are seeing that we're getting precipitation, or rather enhancements in the electrons at around about the KeV level. We might expect that to be a little bit higher given some of these observations but this is suggesting that we've got a hot plasma here, which is coming down to give these at least these striations and this pulsating aurora within the torch feature. So what gives it that wavy feature? Why does this sort of this band, this auroral arc start to have these features in it? And one of the things that's been postulated is maybe it's the Kelvin-Helmholtz instability. And so if we take observations, say from the Swarm spacecraft, and this was a paper by Liu et al. In 2018, and you pass over an omega band, then you do indeed see an enhancement in the drift velocity in that region. So we are seeing enhanced plasma flow associated with that. And indeed, we see this in the Superdarn data as well. If you take these observations, you can see we have a region of very fast flow abutted to a region where there's almost no flow going on whatsoever. But this is actually a ubiquitous feature for quiet arcs. If we look at more and more swarm overpasses, even over a quiet arc, we see this enhanced velocity feature. So seeing that velocity enhancement is not necessarily telling us it's the Kelvin-Helmholtz instability. We need more feeding into that to tell us that that's what's going on. Now, as mentioned earlier, mapping is problematic. Getting it back out to the magnetosphere is somewhat problematic. But if we look in data from the ground and from the ionosphere, and this is again using that SECS technique, there was an omega band passing through here. You can see it in the auroral image. Then actually what we see is that this is appearing at the boundary between the upward and downward current systems. So it appears to be at the region 1, region 2 boundary. So that gives us something that we can go and look for in the magnetosphere to tell us potentially where that source region is. Now, as I mentioned, we do have this shear flow, but if you look in the theory, the suggestion from the theory is actually that this region should be relatively stable to the Kelvin-Helmholtz instabilities. But if you modify this, and you have to bring the ionosphere into this, this region might be unstable to a modified Kelvin-Helmholtz Rayleigh-Taylor instability. And I'll point you to the papers by Yamamoto et al. To find out more about that. So it might be KH instability, it might be a modification of that, but there might be more going on as well. And one of the other suggestions is that these fast flows, these bursty bulk flows that drive streamers that come out of PBIs might also be the source of omega bands. Now, the omega bands form, they also deform as they go, as they propagate round, but they're not necessarily periodic within the oval. And so we might not be seeing a wave growth, we might be seeing something else. And so we have this observation, and we do see this. This is a paper by Henderson et al., where we have streamers coming down, and after the streamer arrives, we start to see torches and omega bands forming in the equatorial oval. So this gives us essentially 3 potential scenarios that we could have for this. The fast flow could arrive, and you can have multiple fast flows arriving at the same place at slightly different times. The flows arrive and they drift eastwards, and that creates torches forming out of the same region over and over again. You could have multiple fast flows arriving from different places in the magnetosphere and arriving at the equator with edge near simultaneously, and that would create a series of torches that then move across. Or you might have some single fast flow which excites some kind of wave growth, and azimuth a wave at the inner edge of the plasma sheet. So the fast flows seem to give us all sorts of possibilities, but we haven't been able to pin this down yet, particularly tracking these fast flows all the way in to see that they might then excite something, and what they excite in the inner magnetosphere that would then be associated with these omega bands remains an open question. So we have this question: what is the role of the shear flow instability or the injection of plasmas? Can we see that these injections are seen, and we see this plasma with the omega bands? If we don't have streamers and we do see omega bands arising without streamers, then what is it that's driving those? And then with regards to the activity level, what is it within the magnetosphere itself that means that these omega bands are seen at higher levels of activities? Is this something that makes it easier for injections to get into the inner magnetosphere, or are there some kind of changes in the plasma in the inner magnetosphere that enhance the Kelvin Helmholtz or modified KH-RT instabilities? Finally, we're going to look at giant undulations. So these are on the other side. If things like omega bands appear on the duskwood side, then giant undulations appear on the giant undulations appear on the duskwood side. The omega bands tend to occur on the dawn side. And again, slight difference that rather than these tongues moving and forming to point inwards from towards the pole from the equatorward boundary, for the giant undulations, these features actually move or form and point equatorwards out of the equatorward edge. Now these are relatively large amplitude, 40 to 400 kilometers, and large wavelength features, and they're perturbations of that equatorward edge of the auroral oval. And these were first reported by Louis et al. In 1982, using data from DMSP, as you can see here. Typically seen in the dusk sector, and they're these protrusions towards the equator. Now they can be seen for relatively long periods of time. They tend to hang around for hours, but they are rather sparsely observed. And a statistical study showed that only 54 giant undulation events were detected during the solar cycle 23. Now, those original images by Louis couldn't tell us where the giant undulations were going, but later, using ASI data, Nishitani showed that we see these undulations. These are in north-south kilograms at different points along, and so we can track these undulations are moving sunwards, and they're moving relatively slowly at only around about 500 meters per second. So nothing particularly spectacular about those in terms of general atmospheric flow. But they also saw that there was this internal structuring. There was something going on inside this region that was moving much, much faster, sometimes double or more of the speed of the undulations themselves, which might give a shear flow. And again, we might be able to invoke the Kelvin Helmholtz instability as something which is creating these waves. If we want to look at these in different wavelengths, we can do that using things like the GUVI instrument on the timed spacecraft. And here we have the different wavelengths where we see that not only are we seeing this emission in electron band aurora, but we're also seeing this emission very strongly in a proton band aurora. And so the indication and the implication was that actually this is a proton signature that maybe leaks into the other bands. And so again, not necessarily a surprise given that we've got protons injected and coming round this way. So we might be seeing high energy protons being scattered by some kind of wave activity to give us this feature in the ionosphere. And again, associated with this, if we've got overpasses by the DMSP spacecraft, for example, we do see an enhancement in velocity, and we do even see an ion drift shear in this region as well, which again might hint at that Kelvin Helmholtz instability. Now, this was a very early idea that maybe the velocity shear between the plasma pores and the returning Dungy cycle convection might give us that Kelvin Helmholtz wave growth. But when this was examined in more detail, it was shown that the instability conditions are not met there. The velocity shear is not strong enough to drive a Kelvin Helmholtz instability simply between essentially the co-rotating plasma pores and the return Dungy convection cycle. However, we now know that that's not the only thing that goes on in this region. And if we look at these observations from Henderson et al., we see just equatorwards of the auroral region, we get these high velocities, these so-called SAPs. We get this high velocity within this, much higher than we would expect from the Dungy cycle. And this might be sufficient in actually driving this region Kelvin Helmholtz unstable. And if you look at the occurrence of these high velocity SAPs with where we see the giant undulations, there seems to be a good agreement between these things. So it does look like that this feature, this SAPS feature in the ionosphere is related to the growth of this wave feature that we see further out. And it also seems to have an impact on the plasma pores. And this is a couple of recent studies from the Van Allen probes. And what we've seen here is that not only do we see perturbations in the magnetic field, and these perturbations match up very well with the propagation of the giant undulations, but these perturbations are associated with perturbations in the high energy proton population. And so it really does suggest a link between these undulations that we see out in the magnetosphere and these high energy protons coming down to give us some kind of auroral feature. Now, this seems to be a positive correlation between one and the other. So we're seeing that when we get these perturbations, we see this enhancement in the protons at high energy here. In contrast, in this study by He et al., it seems like we get this dropout in protons here. So not quite sure how these two things are linked together, but we do think that we're seeing a variation, possibly even a variation in the entire edge of the plasmasphere, and that is being related to these undulations in the auroral features. But we do have to resolve this link between the waves that are seen growing here, the waves in the aurora, and these SAPS processes. And so we do have questions as to what provides the long-lasting giant undulations, how do we get these things lasting for several hours, and then what are the plasma conditions in the source regions, and can we get the instability, the Kelvin-Helmholtz instability supported? And then finally, what is the link between the giant undulations, these SAPS channels, the plasma pores, and the high energy protons that we see out there, that we see these similar features in all of them. So that was all of the features that we've considered. I'll throw this just up in terms of saying that we're looking at features around about the tens to hundreds of kilometers, stretching from the poleward boundary through the auroral oval, and then into the equatorward portion of the oval. And we've got dawn side and dusk side features, and then we've got these features that appear on quiet arcs or existing arcs in association with substorms. If we look through the potential drivers, we see fast flows coming up quite a lot, potentially causing something. And then we also have these instabilities. And the big thing for me is actually pinning down what instabilities can and can't happen in these different regions and getting an idea on that. And in terms of the locations, we go right out from the plasma sheet and the deep tail into the inner magnetosphere, the near Earth magnetotail, and right into the inner magnetosphere. So just as a sort of summary of some of my thoughts and some of the thoughts that came out of this review, we generally see that these dynamic auroral forms are linked to some instability in some way. So let's think of reconnection as an instability, and then PBIs and streamers are resulting from this instability. The omega bands, the torches, all of those undulations on the aurora might be associated with a Kelvin-Helmholtz instability, or maybe some ballooning instability or something else going on in the tail. And then these auroral beads seem to be linked to either ballooning current instabilities or some alphanic instability in the midtail. And what seems to be a problem is simply fitting the growth rates and the scale sizes isn't sufficient to rule these in and out. We've got to do this. We have too much going on in terms of the parameter space for the underlying plasma conditions. So we've got to get a better handle on that in some way. And it might well be that some of these observations are already out there. Observations in the inner magnetosphere or in the midtail on the right scales that we just haven't looked at yet through the Themis mission, the cluster mission, the polar mission, all have passed through these regions, but maybe we've missed some of the important observations there. But it may also be true that those observations aren't there. We're not going to get the right scale sizes, and we're going to need dedicated multi-scale missions in order to get a real handle on these processes. And the last thing, and this is really a challenge going forward for things like machine learning, is how well can we identify and isolate these forms of the aurora in order to do statistical analysis. There's very few statistical analyses of these features out there because they're very hard to identify, and you almost have to go through and do it manually. It's very difficult to do that, at least in a very unbiased way, in order to provide you with enough statistics to look at. So how can we do this? How can we build up the right techniques and tools in order to give us a better idea as to when these things occur, under what conditions, and what they do and do not occur with in the magnetosphere? It's not sufficient to say that we see one form of aurora, or we see something in the magnetosphere and we always see that form of aurora when that thing is in the magnetosphere. What we've got to look at is, do you see that form of aurora when that thing isn't in the magnetosphere? So can we fill in the rest of a truth table to tell us really what's going on? So as I said at the start, this is an overview of a review paper that was published in Space Science Reviews in 2020. The QR code will take you to that review paper. I do encourage you, if you have questions, to go and look into it, because there was far more information in that. And also go and have a look at the other reviews associated with that on the different forms of aurora studied by the different groups. Thank you very much.
Thank you, Colin, for a really detailed review. That was great. So thank you very much. We do have a comment and one question right now. So Joachim Byrne comments on the persistence of auroral streamers, which was at the beginning of your talk. He mentions, if the magnetic flux tube is sheared or twisted by a flow in the tail, the twist and the field line current portion may persist longer than the flow burst. So I think that came up as one of the questions that you had. Lynn Wilson has a question regarding some of the instabilities. Has anyone looked at the filamentation or kink instabilities for the fluctuations that we see in auroral arcs?
I don't remember seeing that, but that doesn't mean that it hasn't been done. We tried to be as thorough as possible when going through this review. I don't specifically remember it, but I would say go away and have a look at, there's a paper by Christina Lynch, which is actually the follow-up to the Meller paper from the Cascades observations. And they did quite a lot of work there, looking at whether, I think it was a tearing mode instability might give you some of those perturbations. So I don't know whether there's any follow-up from that. That's not something that I can say off the top of my head that there was definitely one that I can put my finger on, but we may have missed it in trying to do this review.
The kink instability rings some bells from what I remember, but I don't remember ever seeing anything about a filamentation instability.
So if I remember rightly, and this is stretching my knowledge back to my PhD, the kink instability is associated with sort of a large scale, wavy up down motion of the plasma sheet. I don't know whether that would be associated with an auroral signature or not. And now that you say that, there might have been some work by, I might get it wrong, I think it was Uritsky, but I could be wrong, that looked at that sort of thing in the late 2000s, early 2010s. So worth having a dig through that. Yeah, that might be interesting, but it is a much larger scale instability, and it might have actually been considered by one of the other groups.
Yeah. So the reason I asked this is in the auroral region, you have these rather large currents going up and down towards the Earth's atmosphere, right? So if you have large field line currents, you can get these types of instabilities. And if you go look at reconnection simulations where they have these types of instabilities, but you look at the movies they make of the currents versus time, and look where they're kind of intersecting the boundaries or wherever they try to visualize this, the way that the currents, the like tubes of current or whatever, move versus time looks very similar to some of the undulations you see in the aurora. So I've been wondering, I bugged someone about this a while back, and they had kind of a similar answer to you, in that they thought, they're like, I haven't thought about that. I wasn't really sure if that's possible or if that's a viable mechanism, but I've been wondering about it for a little while. I don't know if it's the the right answer or if it's even plausible, but I assume there's some threshold you could probably estimate, and I just don't remember it. But
well, we certainly have to remember that this is, it's a massively coupled system. The plasma sheet, the motions that occur in the plasma sheet, any propagation of waves within the plasma sheet is presumably going to have some impact on the inner magnetosphere in some way. I mean, that information gets transferred around. So yeah, it's certainly an interesting, intriguing idea that maybe we have missed that. Maybe it's a much larger scale feature within the magnetosphere, which is driving these perturbations, as opposed to something much more local to where the aurora actually happens.
So we are just over, but I have a quick question from your last slide. You mentioned multi-point observations and missions for the future. Do you have an idea of what that might look like?
Well, certainly, there's one on the horizon in terms of helioswarm. If the orbits for helioswarm are right and bring them into the right region, then we might get some feeling on of some of the scale sizes for that. We're also developing in Europe the Plasma Observatory mission, which is going to be a 7 spacecraft mission, which is actually going to target these sorts of regions. So, can we get both down to the ion scales and out to the MHD scales to see these things? I mean, the question with a lot of these is, can we get things like the gradients right? Can we get the observations in the right place? And a cluster was great. I have to say that I'm a UCL person. I think it's written into my contract. But it did give us a lot of observations at different scales in different places. But we never got that overlap of scales. Not fully anyway. We had 2 spacecraft far apart, 2 spacecraft together. But to get that fully 3D measurement of all of the gradients, the necessary gradients of those different scales, we haven't had that yet. And I think we need to do that. And we need to be targeting that, not out at the old traditional 20 RE downtail, because we think that's where the reconnection type region is, but really getting into these interesting regions, at that boundary between the plasma sheet and the inner magnetosphere, coming into that sort of region to see what's going on there. Because it seems like a region that we've largely spent time sending spacecraft through, but not really looking at in detail. And if you want to know what's going on in the equatorward part of your aurora, then that's the region that you've got to look at.
Yeah, cool. Thanks, Colin. So that's everything that we have for today. Our next seminar will be Maria Wallach, and she will be following up with Colin's, talking about the interaction of the solar wind with the tail and the dynamics of the tail and the larger scale dynamics of the aurora. So we look forward to that and I hope to see everyone next week. Thanks again, Colin.
Thank you.